Hello, welcome to this video. In this tutorial, we are going to be discussing how we can find the effective mass of a string, or how we can of a spiral spring, okay, and then or how we can just get a few things. Still on the aspect of, on the discussion of being able to convert the non-linear equation into linear equations, and also deducing some facts from them. So still on that matter, and this is like the third video on that same matter. Okay, so yeah, in this video we talk about a spiral spring. So we're trying to like find the spring constant and the effective mass of the spiral spring. So what we have here is a spring, is a retort stand, and on the retort stand we have a spring hung on it, and then some mass at the end of that spring. Okay, so this particular mass that is hung at the end of the spring is called the varying mass. The varying mass. So that's the English I just used for it, for you to understand the fact that the mass continues to change. Like we can, at the first experiment or the first instance, we might add a mass of 10 kg. Then when we put a 10 kg mass, okay, we pull it down a little bit, give it a slight displacement and release it. So it begins to oscillate. It goes up and down, goes up and down. So we record the time that it will take it to cover 20 full oscillation. That is 20 go come like that, you get, and then we record it. Okay, so then the period is that time, whatever time that we eventually got, divided by 20, because period is the time for one oscillation. So if 20 oscillation took a particular amount of time, then one oscillation will be that amount of time divided by 20. You understand it now? So that is for the period of oscillation, you know, and all. So, but at the end of everything, okay, so sorry, before that, you know, when you do that for a particular value of mass, the precaution or the instruction of the experiments is that you will add another mass to it. Maybe you add another 10 kg, so it becomes 20 kg. You allow it to oscillate again. You add another mass again, you allow it to oscillate, but you are recording the value of the mass at every instance, and then also recording the time it takes for 20 oscillation. Okay, so that is what this experiment is all about. I know you must have done it also in the lab. Okay, so as it is now, if we want to work with what we have here, the mass of the spring itself, when without it carrying any weight, the spring itself has a mass on its own. That mass is called the effective mass of the string. It's called what? The effective mass of the string. The mass of the spring itself is the effective mass. Then this one is the varying mass. Do you understand? And then apart from the effective mass, then we also have the stiffness. The string has a particular constant called the stiffness of the string, represented as constant K. Do you understand? So K signifies the stiffness of the string, while M is the mass of the string itself, which is the effective mass. And this small m is the varying mass. Okay? That is the mass we keep changing, the mass that we keep changing along the line of the experiment. Okay? So obviously, the more we add mass, mass to this stuff, the more the mass, the slower the oscillation. You know, when it is carrying only a little mass, the thing will oscillate faster. Okay, so this is beginning to tell us something that the graph is probably going to be a negative graph. Let's see how it goes. So the equation surrounding this graph itself, the period of oscillation, is given as 2 pi root big M plus small m over K. All right? So we have 2 pi root M plus M over K. That is the equation that governs this experiment. All right? Where big M is the effective mass of the string, small m is the varying mass. Okay? The mass that you keep changing. Okay? Maybe you started with 10, then the instruction will say, okay, after you have recorded the time for 20 oscillation with a mass of 10 grams, okay, then add another one to it again. Maybe another 10, making it 20. You allow it to oscillate 20 times 2, then add 30, add another 10 to it, making it 30, allow it to oscillate. So you could do that for like 5 different values of mass, of values of mass, and then keep recording the value in each case. And then you find the value of t and all that. And then, oh my God, sorry about this. This square is not there. It came from the previous, So it's just normal t. It's like normal t. It's not t squared. I beg your pardon, please. So it is t is equal to 2 pi root m plus m over k. The square comes in when you are trying to remove these roots, and then you square both sides. But naturally, this is the formula for the period of oscillation that of a mass that is hung on a spiral spring. Okay, so that is that as per that. Okay, now let's do the normal thing we do. We want to remove these roots so that we can be able to convert the non-linear graph into linear graph and then make some kind of important deductions. So let's go. So squaring both sides, so you have t squared is equal to, you square this and you square this, that's 4 pi squared, okay, because 2 squared is 4, then pi squared, and then the square will also remove the roots, and it will remain m plus m over k. Okay, so having done that, we have t squared is equal to 4 pi squared m, we have 4 pi squared big M plus 4 pi squared small m divided by k. So you split it across the two terms in the numerator, you split k across the two terms, so you have 4 pi squared big M over k plus 4 pi squared small m over k. So having those two stuff, okay, then you can compare. You can now compare, okay? If you look deep into this, the period of oscillation changes across the experiments. So it is a variable. A variable is anything that can change. The mass, the hanging mass, the mass that you are hanging on the spring or the varying mass also changes across the oscillation, so which makes it also a variable. But apart from the period and the mass, every other thing we can find here, they are constants. The mass of the string remains the mass of the string throughout the experiment. That is, the spring itself has its own mass. So it remains the same throughout the experiment. Okay, the only thing that is changing is the mass that you hung on it. But the spring itself has a fixed value of mass, so it is constant. 4 is constant, pi is constant. The stiffness of the string also is constant. It does not matter the mass of the string or the mass that is hung on it at any given instance, it maintains the same value of stiffness, the hardness of that string. Okay, so the hardness of the spring is given as k, which is a constant value as well. So this one is constant, 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 constant. So the only two variables we have is t squared and m. So if we compare all this scenario here, you have something like y is equal to c plus mx, okay? Meaning because this y is like t squared, because we are going to be plotting a graph of t squared against m. So which means we are going to have a graph like this, a graph of t squared in second squared against m in what? In grams, okay? Against m in grams. And then, so which means because m is a variable, so we take it as our x, okay? And then y is also a variable, but every other thing is constant. So which means our c is this, the intercept is 4 pi squared big M over k. And then plus 4 pi squared over k on its own, this 4 pi squared over k stands as the what? Is equivalent to the slope of the graph. So the slope of the graph is 4 pi squared over k, And then this M here is what is standing as our X, is what stands as our X. So that's our independent variable. Why the dependent variable is t squared. So remember, the independent variable, because you keep changing the value of M deliberately across the experiment. But the value of t depends on the amount of mass that you hung on it, because the heavier the mass, the smaller the value of t squared, which is the period, or the value of t on its own, which is the period. Do you understand it now? So that's how it goes. So this is the independent variable because its value changes independently, but this one depends on this, which is whatever the value of M is that determines the value of t. The mass is at any given instance is what determines the period of oscillation, because the more the mass, the shorter the period, and the more the mass, sorry, the longer the period, and then the smaller the mass, it oscillates faster when the spring is light, okay? But when a heavy substance is on it, it oscillates slower. So which means that this depends on this, because this is what determines the period. Okay, so, all right, with that settled, we have the O, which is the origin, all right? So it shows to us that this is an experiment that produces a positive, the slope is positive, so which means the graph will go upward because the value of the slope that we have here is positive. Do you understand? So it shows to us that the graph slopes upward. Okay, it's a positive graph, it has a positive slope, and then it also shows to us that the slope of the graph is equivalent to 4 pi squared over k, so which means we can be able to determine the stiffness of the spring with the help of the slope of the graph. All right, and then how do we even determine the mass of the spring itself, the effective mass of the spring? Well, the effective mass of the spring can be determined from the intercept, from the value of the intercept. So definitely, if you plot the graph has a positive intercept, so it's something like this. It's more of something like this. The intercept is positive across the t-squared axis, okay? Positive across the t-squared axis, and the intercept is giving us 4 pi squared big M over K. So from the intercept, you can be able to find the value of knowing the value of K from the slope, then we'll be able to find the value of M from the intercept and all that. Then the slope of the graph, let's say, okay, just any 2 points across the graph can give you the slope, any 2 points. It can even be this point and this point, no problem. You can draw your slope triangle, connect the 2 points, okay? At this point, let's say this is point A or point B. Anywhere can be point A, anywhere can be B, okay? So the difference in value of here gives us the change in t squared, while the difference in value here gives us the change in what? In the mass. So which means that slope is equal to change in the t squared divided by change in mass. That is change in y over change in x, all right? And then which is equivalent to this, that is 4 pi squared over k, all right? So if you jump to this video and you didn't watch the previous videos, especially the video 2 in this series, you might not really understand what is going on there. But I took time to explain the whole thing in that video because I know we are going to require it across the rest of the whole thing having to do with graphs as far as this course is concerned. So you may have to refer to that video to learn about straight line graphs, okay, which is the video 2 in this series. Okay, so let's come back here. So the slope of the graph is this, and then but did you notice something? That at the intercepts across the x-axis, at the place where the graph cuts across the x-axis, at the point where the graph cuts at the x, this is the intercept, on the M axis. The intercept on the M axis, that is M measured in grams. What happens here? If you check this out very well, okay, so first we have agreed that slope is equal to 4 pi squared over g, right? And we have also agreed that the intercept at the t squared axis is equivalent to 4 pi squared m over k. But now we want to know what's going to happen at this intercept here. If you look at it, the place where the graph cuts across the x-axis, which is the mass axis, okay, then the value of t squared at that point is what? Is 0. So at the intercept on the m-axis, you say that t squared is equal to 0. So if you know that t squared is equal to 0, you now say therefore 0, which is t squared, 0 is equal to 4 pi squared big M over k, all right, plus 4 pi squared small m over k. So you send this to the other side, all right? If you send any one of them, you decide to send to the other side. Okay, let me decide to send this one to the other side. It becomes negative. It was positive before. By the time it gets to the other side, it becomes negative, right? So which means we are going to be having minus 4 pi squared. That is 0 minus 4 pi squared small m over k is equal to 4 pi squared big M over k. Okay? So 4 pi squared can cancel out 4 pi squared. That is, everything here can cancel everything here. Mathematics allows it. So at the end of the day, you have minus m is equal to big M. Okay? That is, this happens. Therefore, minus m is equal to big M, all right? Is equal to big M. As t squared is equal to 0. So, which means at the, or let me just say at the intercept, on the M axis. Okay? So, any value of M here, any value of M here, on this line, any value of M here is equivalent to the effective mass of the spring. So which means that the slope of the graph can be used to find the stiffness of the spring, which is K, all right? So you can obtain the value of K from the slope of the graph. All you just need to do is cross multiply. Just say K will be equal to 4 pi squared over the slope. And then you are good to go. So you'll be able to get the value of K from the slope of the graph, and then you'll be able to get the value of M, either from the intercept, knowing the value of K, and then you do those mathematics, or directly on the intercept on the M axis. So whatever is it that the value of M is here is equivalent to what? The effective mass of the spring. That's what we're just trying to say. That the effective mass of the spring can be found at the intercept on the Y, on the M axis, okay? All right, mathematically, let's just assume that the intercept is equal to, let's say the value of M here, the mass here is like minus 20. You know, this side is negative, this side is positive. So let's say the mass here is minus 20. If you plot it on the real graph and you are able to know the value of mass, we are using an assumed value now that the value of mass here is minus 20. So therefore, if M is equal to minus 20 at the horizontal intercept, that is the intercept on the horizontal axis, okay? This is the vertical intercept, that is the intercept on the vertical axis. So if M is equal to minus 20, let's just assume, therefore assuming M is equal to minus 20 at the horizontal intercept, okay? Then you have it that what? Minus of minus 20 is equal to what? m, which is the effective mass of the string. Since we already know that minus m is equal to m, so anything that we have here, negative of that value, is equal to the effective mass of the string. So we add 20, minus 20 here. So negative of minus 20 is equal to m. So therefore, the effective mass of the string is minus 20 minus is plus. So we have positive 20 grams. So that is what happens, which means anything you see here, just remove the negative value. Whatever you see there is automatically the mass of the spring of that experiment. The mass of the spring, I've rubbed it off. Spring has gone. So the mass of that spring, okay, the effective mass of the spring is equivalent to the mass of, to the value of m, the mass at this horizontal intercept. So that is what we are able to derive mathematically, okay? All right, so that is that aspect. So all these key informations are very important. All these key information are very important, very, very important to you, all of them. Okay. So you'll be having questions that will be asking you, okay, what happens to the effective mass of the spring when the graph of this t squared against m intersects the m axis? Technical questions can be asked based on your understanding of all of these scenarios. So it is very important you just know exactly what is going on. So I'm going to make another video where we'll be solving questions related to all of these things that we just did. But first, I just need to explain through the material before we start solving questions. So by the time we start solving questions, you understand exactly what every part of the question means, or how the approach to it, or the right answer to those questions. So that's my target. All right. So, and then don't forget the 4 things of Emostel Academy. Our 4 keys is for you to learn. Number 2 is for you to understand. And then number 3 is for you to practice. And number 4, excel. Don't forget that. So I see you in the next video. Bye.